Hello and welcome to this first VMK in the C++ series. I've decided to start this series off so that I have a place to put videos that pertain to C++ specific topics. Now, there are a lot of C++ code we're working with inside of the OpenGL game engine series. However, I want to sort of have this general section here where I can cover different concepts which don't necessarily pertain directly to the game engine. I'm going to start off in this VMK by discussing number systems. I don't have a direct plan as to what's going to be going into the C++ series, but if you guys have any C++ specific questions, feel free to send me an email and then I can create a VMK for you that covers a specific topic you're interested in. Alright, so number systems. We'll go into PowerPoint here, and I put together a few slides to start off the discussion in number systems. You first have to understand how a computer works before you can effectively control a program. Computers store data using a binary number system. This means that all data is made up of ones and zeros. Before I get into the binary number system, which I want to cover in a little bit of detail, let's first go over the decimal number system, which everyone should be familiar with. I should mention here that inside this PowerPoint presentation, anytime I refer to a decimal number, I will highlight it in blue. Anytime I refer to a binary number, I'll highlight it in green, and anytime I describe a hexadecimal number, it will be sort of an orange color. So to start off with the decimal number system, we all know that the number system has 10 base states. The values of these states are represented by the digits from 0 to 9. So you see we have 10 of those. We can use this number system to write numbers like 14, 1234, 3.14, etc. When we look at a specific number, like let's say we analyze the number 14, we can actually break it down into different parts. We have the 1, which part of the 14 here, is actually 1 times 10 to the power of 1. And the 4 here is 4 times 10 to the power of 0. If we multiply this out here, we get 1 times 10 plus 4 times 1, and when we add these together, we get 14. That's how we break down a number into its number system. Now, every number can always be comprised of the sum of the state's values multiplied by its weight. So let's analyze another number like 1234. That's 1,000, which is 1 times 10 to the 3, 200, which is 2 times 10 to the 2, 30, which is 3 times 10 to the 1, and 4, which is 4 times 10 to the 0. So there you go, you get 1 times 1,000, 2 times 100, 3 times 10, and 4 times 1. And again, you can add all of those up and you get 1,234. Another example is with the decimals here. If you had 3.14, the exact same thing applies. We have 3 times 10 to the 0, 1 times 10 to the minus 1, and then 4 times 10 to the minus 2. 10 to the 0 is 1, 10 to the minus 1 is 1 divided by 10, which is 0.1, and 10 to the minus 2 is the same thing as 1 divided by 10 squared, which is 0.01. Again, we can add up all these pieces and we get 3.14. Notice that the decimal point plays an important role in a decimal number. It determines the exponent value of the weighted term. So the weighted term is always the state value times the base to an exponent value. And again, the exponent value comes from where this state value is located with respect to the decimal point. So if we have numbers in front of the decimal point, we have the exponent value starting at 0 and goes up. And if we have numbers starting after the decimal point, then we take the exponent values will be minus 1, minus 2, minus 3, and so on. This rule works for all different number systems, so memorize this rule here. If you understand this, you should be able to understand how to break down any number in any number system. So now let's take a look at the binary number system. The binary number system has only 2 base states, and the values of these states are represented by either 0 or 1. We can use this number system to write numbers like this: 10, 1101, 10001, etc. Notice that all these numbers only have the digits 0 and 1. How much is the number 1101 in decimal? Well, we can convert this using the rule we had on the previous slide. We can take each number, so we'll take this first number, 1, times the base, and because our base here is 2, for a binary number system we have 2, and then we apply that to the exponent of some number. And the exponent determines by where the location of the decimal point is. Decimal point is right here because it's not visible, so we'll have 1, 2, 3 spots moved over to the left, so we have an exponent of 3 here. The next one here has 2 to the exponent, the 0 here has exponent of 1, and the first one here has exponent of 0. So again, we can work this out. We get 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1. And when we add all these up, we get the number 13. So this number 1101 in binary is actually 13 in decimal. Converting from binary to decimal is easy when you remember the rule that I showed you in the previous slide. So this is the rule here. Just take the state value, multiply it by the base to the exponent of wherever it's supposed to be. We add up all the individual components and then we get the decimal equivalent. Careful when you try to convert numbers such as this, 210. If someone tells you 210 is a binary number, they're lying to you because it really isn't. It can't be a binary number because it has the 2-digit in the number. And as I said before, in binary you can only have zeros and ones. So this is not a valid binary number. Let's convert a decimal number to binary now. So we're going to go the opposite direction. Here we went from binary to decimal. Now we're going to go from decimal to binary. How would you represent the decimal number 54 in binary? I'll show you how to convert this in 2 different techniques. The first technique is the one that I prefer, since the method is more intuitive to me when I convert numbers by hand. The second technique is good to use when you're automating the conversion process for a computer to do. So either way, you can do it, but one way is easier to program than the other. Okay, the first technique. We know that the final binary number will be a weighted term sum that looks something like this. It will be some number times 2 to the 3 plus some number times 2 to the 2 plus some number times 2 to the 1 plus some number times 2 to the 0 and so on. Effectively, we can create a table that looks sort of like this, where we have 2 to the 3 is 8, 2 to the 2 is 4, and so on. Now, we may have more numbers to the left and more numbers to the right, but we'll just stick with these ones for now. To begin, we look for a number that is closest to our target number without exceeding it. In our example, we've chosen to work with the number 54. So we're looking for a weighted value that's close to 54, but not over 54. Well, if we look over here, 2 to the 6 is larger than 54. So we know we're not going to have that one there, so I put a 0 in here. 2 to the 5 is equal to 32. So that's less than 54, so we'll put a 1 right here. We can then take 54, subtract 32 from it, because that's how much we just finished adding here, and we now have 22. Now we just repeat the process. We want to find a number that is closest to 22 without going over, using these values over here. Well, the next value over is 16, which isn't greater than 22, so we're going to add it as well. So we put a 1 in here. We take 22 minus 16, we get 6, and we repeat the process. Well, 8 is greater than 6, so we don't want an 8, so we put a 0 here, as you can see. 4 is the next one, which is less than 6, so we do want to use it. So we put a 1 in here, and we get 6 minus 4, which is 2, and we repeat the process again. So now we can see, okay, well, the next one down is a 2. We need a 2, so we're going to add in a 2 here, so we put a 1 in here. So we get 2 minus 2, we get no remainder, so we can fill in zeros everywhere else. And the result that we get here in this table is our binary number. 110110 is actually the binary equivalent of decimal number 54. That's the way that I do it in my head when I'm trying to convert numbers into binary. A simpler, quicker method that you can program is the following. You can take the number that you want to convert to binary, divide it by 2. It equals 27 with 0 remainder. You then take 27 divided by 2, and you get 13, but there is 1 remainder. You just continue doing the process. 13 divided by 2 is 6 with 1 remainder. 6 divided by 2 is 3 with no remainder. 3 divided by 2 is 1 with 1 remainder. And then 1 divided by 2 is 0 with 1 remainder, this one here that you had. So now that you have this number here, you can read it upward. And you get 110110. And you notice it's the exact same number that we got from the previous technique. So both of these techniques work, but one of them is a little bit more intuitive than the other one. This is just sort of like a formula you can use to calculate your binary number, whereas this one is actually stepping you through and making you understand what each of these numbers here represent inside of a binary number. Now I'm going to show you a quick method to write out the binary number sequence. Every now and again when you're working with binary, you may have to write out the binary numbers from like 0 all the way up to 16 or 32 or whatever. Well, there's actually a trick that you can learn to write out the numbers very quickly, and you don't have to like remember, oh, this is 1, this is 2, this is 3, and so on. For now, take the numbers from 0 to 8 and convert each of these to binary. When you do, you'll see you get the following. You get 0, 1, 1, 0, 1, 1, 1, 0, 0, and so on, all the way up to 1, 0, 0, 0. Do you see any pattern in these numbers up here? Look very closely. If you fill in all the previous numbers here with leading zeros so that they're all 4-digit numbers, you get the following. 0, 0, 0, 0, 0, 0, 0, 1, and so on. Now do you see the pattern? Look in the columns of each of these rows. Notice what happens. You have 0, 1, 0, 1, 0, 1, 0, 1, 0, and the next one would be 1. Next one over is 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Next one over is 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, and so on. Every time you move over in a column, you increase how many times the 0 will appear. After it appears a certain number of times, that's the same number of times you have to write down the number 1, and then you flip again. So that's a quick way you can use to write out any binary number sequence sequentially. Alright, now hexadecimal numbers. Binary numbers you'll use inside C++, but you won't actually, how can I say this? You won't use the numbers directly. Instead, you'll use the bit representations of variables in binary form. And I can talk about this a little later, but in this video I want to focus on hexadecimal numbers. Hexadecimal numbers you'll experience more frequently, I think, in C++ when you're working with hardware. A lot of times hardware is programmed in such a way that memory addresses are hard-coded into a piece of hardware, and you need to access that hardware. To do that, you need to understand how to convert from binary to decimal to hexadecimal and all the way through. So you need to be able to understand the different number systems quite readily. Hexadecimal number system has 16 base states. The values of the states are represented from the numbers 0 to 9, and then we add in the 6 first letters of the alphabet, A, B, C, D, E, and F. The weights are 0 to 9 are obviously between 0 and 9, and then A has a value of 10, B has a value of 11, and so on, all the way up to F having a value of 15. You can use the hexadecimal number system to write numbers such as this, 3F2, 1345, AA, things like this. Any character that you see here is a valid number that you can use in the hexadecimal number system. So AA is actually a number. 1345 is actually a number. And we'll convert these to decimal so you can see what these mean. To convert to decimal, you apply the formula I showed you before, where we take the state, multiply it by the base to the exponent, and add it to all the other parts. So if we're looking at F2A, we have F times 16 to the 2, we have 2 times 16 to the 1, and then we have A times 16 to the 0. F is the same thing as 15, so we plug in 15 here, and 16 squared is 256. 2 is 2, so we have 2 times 16 to the 1 is 16, and A has a value of 10 up here. So we have 10 times 16 to the 0, which is 1. And when we add up all the numbers, we get 3,882. So in hex, F2A is equal to 3,882 in decimal. There exists a very useful relationship between hex numbers and binary numbers. every hex digit is equal to 4 binary digits. So you can see here, if we take all the hex numbers from 0 all the way to F and write out the binary number equivalent, we can see that, the letter A is equal to 1010. The letter D is equal to 1101. The letter 4 is 0100. Using this, you can convert any binary number to hex or vice versa, hex number to binary. You just have to remember this table here. So let's take a look at this number here. We have 10110111. What is this binary number in hex? Well, when you work it out, the answer is B2. And the way you do this is basically, imagine splitting this binary number right in half. You got 1011. Look up at this table here and you see 1011. That's a B. So we'll write down B. 0111 is over here 0111. That's 7. So you get B7. We can convert this number here in binary, 101001, to hex, and we get 29. And the way we do this is, again, we draw an imaginary line right here, splitting these two numbers with these 4. We always have to group the binary numbers in groups of 4, but we group them from the right-hand side, working our way to the left. So we take the first 4 numbers from the right-hand side, group them, and then we take the next ones. If you're missing some numbers, just add in zeros at the front. So we have 1001, and looking at this table here, 1001 is 9, and then we'd have 0010, so 0010 is 2. That's where I got the 29. So here's a summary of number systems. If someone offers you some money and they say that you can have $10010 in any number system that you would like to use, what would you prefer to use? In decimal, we know that 10010 would be $10,010. In binary, 10010, if we were to convert this to decimal, we would get the following, which is $18. So the same number in binary would actually be worth less. If we take that same number in hexadecimal, convert it to decimal, we see it's worth $65,552. So really, hexadecimal is a very sort of dense number system. And it's dense because it has 16 base states, whereas decimal only has 10. So we're able to squeeze in more values for a specific number. So in conclusion, make sure you understand what number system you're using, because the same number can mean different things depending on which number system you're using. As you see here, a 10010 in decimal is this much, in binary is this much, and in hexadecimal is this much. Now, to help you work with number systems in C++, I wanted to go in here and actually show you how to take a look at different number systems within C++ itself. We'll start off by just creating a very simple project. So we'll go into a new project. We'll create a Win32 console project, and I'll call this test numbers. Doesn't matter what you call it. And under application setting, make sure you've got console application selected and nothing else here. You'll create a main program here where we're just going to create an integer value, I value, and I'll set this value up to be equal to 1, 2, 3. Now what I'm going to do is I'm going to print this value out to the screen so you could see it using the standard technique like so. Oh, I'll also put a carriage return at the end here just so it's a little nicer to visualize. Now Control F5, build it and run it, and you can see the value is printed to the screen 1, 2, 3. The value you're seeing is actually the decimal equivalent because we've chosen the D letter here. With the printf function, as well as all the other functions that work the same way as printf, you can use D to represent decimals. If you change this to an X and still pass in the same integer value, now when you run it, you'll notice that you don't get 1, 2, 3, you get 7B. 7B is actually the equivalent in hex for 1, 2, 3. And to prove this another way, we can go into Windows Calculator here, and by default you should have decimal selected here. We can type in 1, 2, 3, and you can see 1, 2, 3 displayed in the display here. But if we go and click on hex, you'll convert that decimal number to a hex number. So you get 7B now. And if I click on decimal, you'll convert it back to 1, 2, 3. You can also go and convert it to binary if you like by clicking on the binary number, and there's the binary equivalent of 1, 2, 3. There's also this other number system here, octal. It's another number system similar to, binary, hex, whatever, but octal actually only has 8 states within its number system. So it only goes from 0, 1, 2, 3, 4, 5, 6, and 7. I don't talk about octal very much because it's not very popular within programming, whereas binary and hex are. So that's basically it. You can also go into C++, and we've defined an integer variable here, but we can define it to be a hexadecimal value. The way we do that in C++ is we use the number 0, a small x, and then we can specify the hexadecimal equivalent. So we know that 7b is 1, 2, 3. So if we do this and we run our program, we should see 7b appearing on the screen, 7b, because we still have the little x over here. Well, if we replace the x with a d, we'll now take this hex number and display it as a decimal. So this will be the equivalent that we did before, 1, 2, 3. One other way you can visualize decimal numbers and hexadecimal numbers in C++ is, let's say we place a breakpoint. We place a breakpoint here, and then we can run our program, which will automatically stop right where we place our breakpoint. Inside of our watch window, if you don't have the watch window here, you can go under, I think it's under debug, maybe? Yeah, debug, and then, let's see, Windows, you'll have a watch, and then you can open up watch number 1. That'll open up this window here. Inside the watch, you can view any value that you have inside memory. So right now we have this value here, I value. So we can just type it in here, I value, and you'll see that the value of this variable is 1, 2, 3. 1, 2, 3, of course, is the decimal equivalent of this variable. If we wanted to view this value in hexadecimal, all we need to do is right-click and select hexadecimal display, and automatically C++ will convert that number for you to be hexadecimal displayed. And you notice that we have that 0x in front, bunch of zeros, and then 7b. So there you go, a bunch of different ways to view decimal numbers and hexadecimal numbers right within C++.